Okay. Well, welcome everybody. My name's Andrew Dunstan. I work for Second Quadrant. And today we're going to be talking about JSON in PostgreSQL. I've been involved in the creation of the JSON facilities in PostgreSQL pretty much from the start. And it's been kind of interesting. If you're not aware of what JSON is, it's essentially a very lightweight data format that provides for a sort of an arbitrary tree structure. It's very widely used as a data interchange format. It's probably gaining a lot of strength over earlier things like XML, which are rather more involved, but you can format data and exchange very easily using JSON. There's an internet standard for it, RFC 7159. There's a lot of information, a lot of useful information about it at JSON.org. If you're not familiar with that, look at the website. It's got some quite useful things, including railway diagrams for syntax and that sort of thing. And also a lot of information about implementations in a huge number of languages and other pieces of software. Essentially, it consists of two sorts. There are two sorts of data values in JSON. There are scalars and non-scalars. And the scalars, this is pretty much the entire specification. You can have these three things, literals, null, true, and false. There are numbers, which are unquoted strings of digits, possibly with a decimal point, possibly with an exponent. And there are strings, which are sequences of characters inside double quotes. The standard actually specifies that JSON should be in UTF-8. Postgres actually allows some other encodings, but if you're going to use it, I'd strongly advise you to use UTF-8. One word about numbers. Some implementations, or many implementations, in fact, treat numbers in effect as either as integers if they don't have a decimal point, or as IEEE doubles if they do. That means that you're limited in the amount of digits and so on that you can effectively have in a numeric data in a lot of implementations. Postgres does not do that. We treat numbers as the numeric data type, which essentially means arbitrary precision. You can have thousands and thousands of digits in a JSON number, and Postgres will deal with it appropriately. I'm not sure about thousands, but certainly many more than you can fit in a standard double. So what's missing? Oh, we'll get to what's missing in a minute. Non-scalars essentially are these two things: arrays, which is simply a sequence of JSON values separated by commas and enclosed in square brackets, and objects, which are sequences of key value pairs. The keys must be strings. The values can be any JSON value, and they're separated by comma. There's a colon between the key and the value, and they're enclosed in curly braces like that. That's pretty much it. That's the whole of what JSON looks like. And you can represent a huge amount of, vast array of different pieces of data just using those constructors. So what's missing is essentially treatment for other data types, things like binary data, date-time types, essentially anything that you can't express any other way, you have to express as a string in JSON, and that is pretty much, that makes it opaque. So for instance, for a picture or something like that, you are going to have to do something like base64 encode it and then put the base64 encoded data in a string. Because you can't put binary nulls and other things in, the string still has to be UDF-8. So that's kind of a limitation if you want to store data like that. Nevertheless, it's still extremely useful, and people do store these types of data in these ways in JSON. So we started with this. The first commit was from a piece of code from Robert Haas, and Robert committed this on January 31st, 2012. So we've been at this for over 6 years. The second commit was something I committed on February 3rd, just a few days later, which provided some facilities to generate JSON out of SQL data. And that's pretty much where we started. So release 11, which is about to come up, is going to be the 7th release in a row where we've had some JSON development in the release. It's an ongoing piece of work. There's more work coming in Postgres 11, and I'll be telling you a little later about work that's coming down the track, we hope, in Postgres 12. And there's some quite exciting stuff happening. This is still an area of active development. So Postgres 9.2, released in September 2012, basically had those things from those first two commits. The basic JSON type, it validated the JSON. So if you handed it a piece of text that was not valid JSON, it would spit it out. The JSON data itself was stored as text. Whatever you put in is exactly what was stored. There were no functions to pull data out of JSON. So essentially you could put JSON in and you get the JSON out, but you couldn't pull out a piece of the JSON. We have the generation functions that I mentioned, and we're going to see those in a minute. And that's where we started. Postgres 9.3, we changed a lot of that. So there was a parser rewrite, which I undertook, and essentially what we did there, what that did was to enable us to create a whole lot of functions to process JSON, to get a value out of JSON, to take apart a JSON array, and that sort of thing, and a bunch of operators. And we're going to see some of those in a minute. Postgres 9.4 in 2014 introduced the JSON B type. JSON B type is essentially takes the same input as the JSON type, but it parses it before it stores it. So it stores it in a decomposed form, and that makes it a whole lot faster to deal with. It doesn't save much in the way of space, but it saves a heck of a lot in terms of processing time. We added some new operators in 9.4, and we added some indexing support. And we also included some standard comparison operators, which don't operate on the JSON type because it's kind of meaningless, and some new generator functions. Postgres 9.5, we added some more functions and operators. JSON B set, which lets you set a value inside a piece of JSON. JSON B Pretty, which pretty prints JSON. And we added some things for concatenation and for deleting data, and also something to strip out fields that have null values. 9.6, we didn't do terribly much. We added a new function to allow you to insert something into a JSON B array. In 10, which was released last year, we included full text search for JSON. We allowed deletion of an array of keys instead of having to delete single values. We enhanced the populate record functions so that they operate recursively, so that if you have a composite inside a value, it would deal with it appropriately. And we handled array pseudotypes rather better. Postgres 11, which we hope will be released, I'm not sure exactly when, but fairly soon, is going to have the following features. It will have JSON-B transforms for PL Python and PL Perl. This is kind of important. It means that if you have a piece of JSON-B, it will map to, if it's an object, it will map to a Perl hash or a Python dictionary fairly automatically. You won't have to do anything. It will just be there in the appropriate way inside your function. And if it's an array, it will map to a Perl array or a Python list. So that's actually kind of nice. We've got some better full-text search because you can create a TS vector from JSON or JSON-B. That makes the text search features work a whole lot more usefully. And some very useful casts from JSON-B scalars to numeric and Boolean types so that you don't have to cast them to text and then to something else. I'll talk a bit later in the talk about what's coming down the track in we hope, in Postgres 12. So, which of these types should you use? We've got these two data types, which annoys some people. In almost all cases, you really want to use JSON-B. Because although the input is a little bit slower, depending on your input, it's 10 to 30% slower, the processing speed is enormously faster by a couple of orders of magnitude. So it's not even close. That plus the indexing support and the extra operators, there's really, if you're going to store the data in a database column particularly, store it in JSON-B. It's almost always what you want. And pretty much that should be your rule of thumb. Don't use the JSON type unless you've got a particular reason for doing so. So here's essentially the difference. With JSON, you get, as I said, it's stored as text. That means if there's white space there, you'll get the white space back. It means that we keep the same key order as you had in the input. And if there are duplicate keys in an object, those are kept as well. In other words, you get back exactly what you put in. JSON-B, it's not like that at all. Because it's pre-processed, we've actually dissolved all the white space away. So that's not there anymore. And duplicate keys are resolved. So the last one wins in the input. That's a fairly standard rule, and it just falls out fairly naturally. And there's a canonical key order. The key order is not preserved within objects. The order is a little bit odd, but it was chosen quite deliberately to make it fast to search the keys of an object. If we want to locate, the value of some key inside an object, this order helps us to do it in a very fast way. And there are some extra functions and operators, as I mentioned, for JSON-B. So in general, this is really the way you want to go. Now, most of the functions that we have exist for both of these types. There's 2JSON and 2JSON-B. There's JSON Each and JSON-B Each and so on. And most of the operators also exist for both data types. We'll see some later on that don't, but most of them do. So let's have a look at some of the functions that exist. Firstly, creating JSON from SQL data. The simplest thing is to JSON. You can pass it pretty much any value out of any literal value, any column value, and it will create a JSON data value for you. And that's pretty useful. The other thing is that we've got these functions, JSON build array, JSON build object, and JSON object, which build up pieces of JSON in effect in a piecewise way. So you can pass any number of arguments to these functions, and it will construct an object or an array out of all the data that you pass them. I'm going to show you some examples in a minute. You can also aggregate data to JSON. So just as you can say to JSON anything, you can say JSON Ag and give it any column or expression, and it will construct an array, a JSON array of the values. It works the same as any other aggregating function like string ag or array ag. But instead of constructing a string or an array, it constructs a JSON array. JSON Object Ag does the same thing, but instead of constructing a JSON array, it constructs a JSON object. All right, so here's an example. We've got this little query here which is going to select the IDs and products from a catalog. In this case, it happens to be a catalog from a pet store. And we pass the results of that, the whole row of that, into JSON-R, and it turns those rows into JSON, just like this, one per record. So that's kind of neat. We could get the same thing by using, instead of using toJSON, we use JSON Ag, exact same query. And we see it's the same result, except here we've got one row produced out of this whole query because all these records have been wrapped in a JSON array. Okay? JSON Object Ag is a little bit different because we have to pass two arguments to it, because an object has keys and values. And in this case, our query is going to produce a set of key value pairs for the inventory out of this pet store catalog, where the product names are the keys, and you can see here that it's produced an object where the names are the keys and the values are the amount of inventory available. So you can construct your JSON in quite a lot of different ways. I'm going to show you something that's a little bit, I've shown this a few times to people, but this is a little bit off the beaten track, but it demonstrates some of the power that we've got here in the JSON functions. Given this data, it's possible to construct a crosstab where the values from column A are going to be the row IDs, and the values in column B are actually going to be the remaining columns in the example. This is something that is done by the contrib module table func, and it looks like this. Okay, so that's the same data more or less rearranged. It's kind of pivot table. So the interesting thing about this is that to run this query, yeah.
So this columns, are they dynamic, or I need to know in advance what their names are?
It's exactly the point. Yes. To run this query, you actually need to know the values in this column B here in order to run this query, because as you can see, we've actually passed this in. We've told this query on the third line of that query what the shape of the data is, and that's the problem, because that quickly gets to be fairly unmanageable, except in sort of toy examples like this. So here's more or less the same query, almost doing the same thing using JSON. But instead of producing this result where we've got these values as the column headers, we've produced JSON results where those values are the keys in our object records. And in this particular query, as you can see, we don't have to tell it what those values are. We don't have to know in advance what the values are in column in column B here, we haven't specified anything about that in this query. What we've done is we've simply collected these two arrays that are ordered by those columns, and then we've passed that into JSON Object, and we've grouped by the values in the first column. And so this is a way in which you could, this is an example that I more or less put together to demonstrate the power of the function of the generation functions that we have in JSON. And this would be something that you could do. As I say, the particular advantage of this is you don't need to know ahead of time what those column headers are going to be. So you can build up JSON piece by piece. Here's an example, or a couple of examples that build. The first one builds an object that is fairly considerable. It's got some nested calls to JSON build object. The last piece of it collects up a record, which it passes to JSON, and it shoves all that together into this long object. Now, this is sort of got a very irregular shape, and this is not the sort of shape that you normally get out of SQL data, but by using these sorts of calls, you can construct pretty arbitrary shaped JSON to suit your needs. Most uses of JSON are not very rectangular. Most SQL data is fairly rectangular, and this is the way that you can convert rectangular data into a very non-rectangular shape. So we looked at turning SQL data into JSON. So now we're going to look the other way. We're going to look at turning JSON data into database rows. And we have these functions with JSON populate record and populate record set. If you're familiar with the HStore module, some of the ideas for this came from that. And we have JSON to record, which is slightly different because here we're actually going to specify at runtime what the shape of the data is. So we're going to have this type here, which is just going to have, did somebody call it? No. So, just going to have 3 fields in it. And so in the first example, we're simply going to specify that we're going to populate this record with from the JSON, and we're going to pass in null of this particular type, ext type, so that it knows what type to return. And here we can see that the JSON has a value q, with a key q with a value true. Now, ext type doesn't have a field called q, so that's just ignored. The x and y values are taken from the input JSON. The JSON doesn't have a z field, and so it ends up as null in the resulting record. Now, if we say JSON populate record set, it expects, instead of a single object, it expects an array of objects in the JSON, and it will provide one record for each object in that array. Here, we've actually done something a little bit different. Instead of passing in a null value, we've actually passed in a partially populated record where the first field has this value blurful, and the other 2 fields have the value null. And you can see that in the second record we've got in this object, there is no x value. So the x value is picked up from the input record, which is a kind of default. In the first record, there is an x value foo, and that overrides the value blurful. So again, this is pretty powerful. the JSON two-record and two-record set functions work in kind of the same way, but there is no record type passed in as an argument. Instead, what you have to do is specify in the call what the output record is going to look like using a type expression rather like this. So there's no notion of passing in a default value, simply saying what the shape of the records is going to be. And the virtue of doing this, and I originally created this because I had a customer who complained that they had to create data types all over the place simply to get data out of JSON in this way, which they only wanted for transient purposes, and it was kind of annoying and bloating up their catalogs. And so they wanted to be able to do this do something like JSON populate record without creating data types. So this is what we came up with. Okay, so now we're going to look at getting some data out of JSON. Am I going for time? All right. Okay. We have these functions, these operators here, and as you can see, they come in pairs. The pairs are the same, except that in each case, the second one has 2 arrowheads instead of 1. If it has 2 arrowheads, then the operator is going to return a text value. If it only has 1, it's going to return JSON or JSON B as the value, which means that, in particular, that you can then use that result for further processing. So it's quite common to see these operators chained using the 1 arrowhead, 1 arrowhead, 1 arrowhead, and then 2 arrowheads at the end in order to get a deeply nested value out of the JSON. So in the first case, if we specify, we're going to specify a key from an object. In the second case, we're going to specify an index for an array. And in the third case, we're actually going to specify a path which is going to be an array of text values that is going to specify somewhere deeply nested inside the JSON. I'm going to show you some examples in a second. All of these exist for JSON and JSON B, and they all operate that way. So here's a simple example. We have this object that has 2 keys. We want to get the A element out, and it returns it. Now you'll notice there's 1 arrowhead here. That means we're going to get a JSON value out, not a text value. And so that means that this is going to be quoted, because without the quotes, that would not be a legal JSON value. In the second case, we're taking exactly the same JSON, but now we're using 2 arrowheads, and the value is no longer quoted because we're interested in the actual text string value. Okay. And in the third case, we're going to get the B value out, and it's a number. It doesn't really matter whether we use 2 arrowheads or not here. It's not going to be quoted. Only string values are quoted, because 1 on its own is actually a legal JSON value, because it's a number. Only strings have to be quoted. So we can also get an array element out here. JSON arrays, incidentally, are numbered from 0. That's pretty standard processing. Pretty much everybody treats it like that. So that means they're unlike arrays in Postgres arrays in SQL, which are numbered by default from 1. So element 0 is the A, element 1 is the 1, and that's returned here in the first instance. In the second instance, it's going to return this piece of JSON, because that's element 5. and it doesn't matter whether or not we use 2 arrowheads or 1 arrowhead. The data type will be different, but it will look exactly the same. Again, only strings are quoted. Yeah. I think it's going to give you back null. Say again. I'm sorry. Well, you would have to get out the 45, you would have to use a path through there. We're going to see that in a second. So if you just use a 5 here, it's going to give you the whole value that's at element 5 of this array. If we want to get something out of that, then we're going to use a path. Okay, here's this slide. Okay, so we want to see. That's exactly what you want to see. You want to go to element 5 and then get the C value out of that array, and instead of use this hash double arrow operator, and you pass in an array which specifies the path, and it gives you out the value. If you only use 1 arrowhead, it's going to give you back the value as a piece of JSON. Okay? The other thing you can do is you can use JSON Extract Path and JSON B Extract Path, and instead of constructing an array of the paths elements, you can simply pass them in one by one. This takes an arbitrary number of arguments, one for each level that you want to descend into the JSON. There's a whole lot of other functions that I probably don't have time to cover. JSON Each, which turns a JSON object into a set of key value pairs. You can get the object keys. You can get the elements out of an array. You can find the length of an array. They're all pretty useful. There are some utility functions. If you want to know whether what the type is, whether it's a number or a string or a Boolean, this function will tell you. And finally, there's JSON Pretty. This function actually only exists for JSON B. Because we dissolve away all the white space in JSON B, this provides you with an ability to get back a nicely formatted piece of JSON text. So there are these operators that this 2 bars operator combines 2 JSON B values, and this minus operator deletes an element. There are also JSON B set and JSON B insert. They would have put this clock somewhere other than there because it would make it a lot easier to see. Okay, here are some examples. In this case, we're combining these 2 objects, and you can see that both of them have an A field. So the one in the second one wins, but the first one has a B, the second one has a C, and the resulting object ends up with both of those values. In this case, we're going to use minus to delete the element A and its associated, the key and its associated value, and we're left with just B as a result. JSON B set is also an extremely useful function. We can use this to set particular elements inside an array or an object. If the element of an array is off the end of the array, then it basically appends something at the end. As you can see here in the last case, we've specified an index of 99, which is way off the end of this array. And so the element that we're actually inserting is simply appended to the end of the array. JSON Beam insert will insert something right in the middle of the array and shift everything out along the end. There's actually another element where you can actually specify whether you want it to go before or after the specified element. So there are some query operators that only operate on JSON B, and here they are. The first one is probably the most useful one, which is the right-hand side a subset of the left-hand side. This is very, very useful for searching. The next operator, probably less so. And there are these other operators that, do we have this as a key? We don't care whether it's a value. Or do all these elements exist as top-level keys, or do any of them exist as top-level keys? Now, the useful thing about this is that you can index these operations, which makes searching JSON values extremely JSON values extremely efficient. We have two types of two operation classes for doing this. The first one indexes most of those operators, but it constructs indexes which are potentially very large. So you want to be careful about using JSON B ops. It's the default class mainly because it indexes most of the operators. But JSON B path ops only covers this sort of subset operation, but it's much more efficient. It's faster. The indexes are far smaller, and that's often what you want. So let's have a quick look at constructing that. Not doing too bad. Okay. You can create these indexes like this. The first one uses the default operator class. You simply specify that you're constructing a GIN index and the column that you're going to be indexing. If you're going to use JSON B path ops, then you actually need to spell that out in the index creation method. You can see that's the second argument here on the bottom line. It's also possible to construct standard B-tree indexes on this, but you can't. You need an expression that returns something other than JSON or JSON B. But for instance, if we wanted to index the author field of the details, just the author field, we could create a B-tree index doing that. That is sometimes useful, but of course, if you want to index author and publisher and something else, you're going to have a whole bunch of indexes, whereas indexing the whole field using GIN is going to index all the fields. So then you need to make sure that you match your query to the index that you're going to use. So if you've constructed a B-tree index, then you're going to construct a query where it looks like this, where the expression more or less matches the expression that we use to construct the index, and the test, looks like this. In the first case, if you have the GIN index, you're going to use this subset operator to search for a field which has got the author, like that. And in both cases, it will use the appropriate index. All right, so that's a look at what we've got today, and what's a brief look at what we've got today, and what's and up to Postgres 11. So now I'm going to talk a little bit about what's coming down the track, because it's actually kind of interesting. There is a new standard, it's a couple of years old, from the SQL committee called SQL JSON. it actually matches quite a lot of the things that we've just looked at, to the extent that they've more or less adapted our names of functions. But it also contains a powerful new query language for filtering JSON. There are some patches that implement most of this. They've been around for a while. They didn't get committed for Postgres 11. But I'm quite hopeful that we will get something committed fairly soon. It's quite a large body of code. It's there's a lot to digest there. So I'm not promising anything, but I'm hopeful. So this the function, the language that we talked about is called JSON Path. It's kind of analogous to XPath for XML. There's actually a new data type in the function for storing parsed JSON path data, and some new query operators for using them. So here are some examples. So in this first example, you can see that it's using this operator in the middle here, at star, and then you've got this weird expression which basically says we want to take all the values of the A element and then filter them. That's what the query says, the question mark says, for any that are greater than 2. So what that is going to give us back is the elements 3, 4, and 5. Okay. So we can then the next thing we can select is it's the same query, but instead of using at star, we use at hash, and now it's going to give us back those elements 3, 4, and 5 as an array. Or we can simply test if it's going to return us any elements at all with at query, and that'll give us back true or false. And finally, we can not filter the rows, but we can simply test if there are any elements greater than 2. So that will also give us back true or false, but it's a different type of expression here in JSON Path. Now, these last two operators can also use the existing indexes, existing gin indexes that we construct. So they're pretty useful. The first two can't use the indexes because they're not really predicate tests. Okay, so JSON Path, that just gives you a very, very brief flavour of what it can do. It can do a whole lot more. It's got regular expression matching. It's got date-time processing. It's got mathematical functions. It's got map and reduce operations on nodes. It's extremely powerful. Then there's coming some JSON functions. There are some constructor functions. These ones here, as you can see, their names are fairly similar to the ones that we've already got, and they have some extra functionality. But you can do pretty much what they do with our existing functions. However, there are some extra functions here. These particular ones, but the most useful are probably going to be JSON Query and JSON Table. The others are there probably more for completeness than anything else. I personally don't feel they're going to be of any great value, but I could be wrong. Here's JSON Query example. This is out of the new documentation, and basically you can see again we've got a piece of JSON script and a JSON path expression is the second argument, and then we've said with wrapper. So basically what this is doing is to tell the function to wrap the results in an array. And it says that if there's an error, throw an error, and there are other possibilities here. So there's quite a lot of flexibility in these functions. JSON table is going to work kind of the same way that XML table does. So again, you can recast JSON data as a piece of SQL data in a very flexible and powerful way. Okay, this is pretty much my last topic. Just about bang on time. When should you use JSON? This is a question I get asked a lot. And pretty much my answer is use it when you have to and don't use it otherwise. Which people often find quite a surprising answer. But so if you don't know what the shape of the data that's coming in is, and quite often people are constructing things like data warehouses where they're going to be getting data in from all sorts of different sources, and you're just not quite sure what you're going to get. That's a really good case for using JSON. But there are downsides, right? There is no referential integrity, pretty much. Foreign keys, you have to match a particular value of a column to a unique index. All right, you can't do that usefully with JSON because it's a composite value, and so you're pretty much abandoning the idea of database enforced referential integrity. You can't use expression indexes for foreign keys, so you're pretty much dead in the water from the foreign key point of view. JSON can take up lots of space. Right? You're storing the keys over and over and over again. Even though we dissolve away white space, we're storing structure metadata in JSON-B, so it doesn't actually save a lot of space. So here are some cases where you shouldn't probably use JSON. Well-defined fields, in very well-defined operations. Finance, commerce, human resources, very well understood fields where you know exactly what the data is going to look like. There's very little reason to use to store data as JSON there. Store it in the fields where you can create really good, efficient, fast, small B-tree indexes. You can get massive throughput there. You're probably never going to be able to get the same throughput with JSON in these cases. Okay, cases where you should use JSON, as I said, where you've got disparate sources, data warehousing applications. If the data's already in JSON or something like it, XML, YAML, whatever, then, again, a good case for storing the data is JSON. So really what you ought to be doing is constructing hybrid applications, use conventional tables where you can, use JSON fields where you need to augment that with data where you're less certain about the shape of the data. Here are some bad reasons for using JSON. I don't like or can't write SQL, and I get people who say that to me, and I say, well, go away and learn. Okay, it's not a good reason for it. I mean, and I've sort of said, oh well, I just want Mongo. Well, go and use Mongo. Or I don't want to design the tables. It's too much work. I mean, if any of those reasons are, Postgres is probably not the product you should be using. But trying to shoehorn things into Postgres for these sorts of reasons, not, in my opinion, a very good policy. Good reason for using JSON, I don't know what we're going to get yet. And I don't want to have to make constant changes to the database. Now, the things I've talked about, JSON Path, SQL JSON, are going to probably make a more compelling case for using JSON. This is really a judgment call, but I think you're going to, this will tilt the balance a bit more in favor of JSON because we're going to get these more powerful querying facilities, particularly with JSON Path. And JSON Table is going to make things pretty nice too. Whatever decision you make, benchmark your applications. Right? JSON can impose significant performance penalties. Benchmark and load test your application, and be prepared to change your application if you need to sacrifice use of JSON and go to more conventional data operations. Here's plea. This is pretty much my last slide. Let us know what you need. I always try to listen to people, about what they need. This is an area that's still under active development. As I said, we're coming up to, I think, the 7th release, and there's still a lot more to go. We try to respond to users' needs. If there are things that you need in this area or any area, let us know because it's extremely useful to us in deciding what to do. So there, I'm done, and I'm right out of time. Thank you very much. Yeah.
Are you going to make your slides available somewhere?
Yes, I will. I'm not sure what arrangements the conference has made. If nothing else, I'll publish them on the second quadrant blog. Yeah.
I have a question about the operators where you have dash, arrow, like that kind of stuff.
Yeah.
Is it possible to use just a function without needing to know? Because I saw, for example, when you want to remove an element from an array with a minus sign, there's one which is JSON set, and then there's like different types. Either there's a function or there's like
there are functions that correspond to the operators.
Okay.
Yeah.
Any plans to support JSON schema?
No, I actually tried to get somebody some people to support it, but I didn't get enough interest. I mean, it could probably be done as an extension to provide a validating mechanism using JSON schema. But it would probably be a deal of work. Yes, yeah.
So that's another question, actually, that's testimony. My team, stand up, please. Okay, so we actually are using JSON Beto, but we never, I want to thank you each time you give these talks, you tell do not use when you absolutely do not have to. And we are actually not using JSON in the database, ever, never, but we are extremely thankful to these options because this allows us to provide transporting data to and from application and real time. The whole system of very efficient conversion of anything in the database to anything in the application and back. So we use like each and single thing, and it's actually awesome that we have it. But we would never ever, because we can do better than manual.
Yeah, sure. All right, yep, one more.
If you've got an actual database with non-rectangular data serialized as string, and you would like to migrate that to JSON, how would you do that? Like, what would you recommend? To try to load the parser as an extension to do the migration, or
I don't know. I would probably do something outside the database to create it as JSON and then load it from there.
And repopulate it?
Yes. Yeah, one final one.
So some of this you mentioned, they all assume that values are strings, right? So there are no ways to tell to create a mapping for JSON fields and use definitions of the type data. So for example, I have date time as fields inside of JSON. Can I create a fields?
No, not really. Well, you could use a cast.
Yeah, but I will create a separate index exactly for that
Yes.
field inside of JSON, right?
Yes, you could do that. You could cast the value to date time and create an index on that. Yes. Okay, thank you.